All right, so now we're going to talk about the Riemannian connection on Riemannian submanifolds. Okay, so let's set up the problem. Okay, so let's say that we have a manifold M, okay, be a Riemannian submanifold. Of a Riemannian manifold M bar. Okay, and of course it's like, if you recall, what that really means is that if you think of something in M, it's like, and you include it, it's like into M bar. Then, for example, if you have two vectors, it's like in M, you can use the tangent lift or the inclusion map to think of them as two vectors in M bar, and then use the Riemannian metric defined in M bar, it's like to induce a metric on M, right? So that's what's meant by it being not just a submanifold, but a Riemannian submanifold. Okay, so as put another way, by definition, right, the Riemannian metric on the submanifold M right, is obtained by restricting, it's like, to M, it's like the Riemannian metric on M bar, right? Sorry. Okay, restricting to M, the Riemannian metric on M bar. Okay. All right. So we're going to use the same, it's like bracket notation for both of them. Okay. Now it's like, similarly, it's like we're going to define, it's like some sort of affine connection on this, actually the Riemannian connection, right? So let nabla be the Riemannian connection for M, and nabla bar, right, be the Riemannian connection for M bar. Okay. All right. And then we're also going to look at, okay. So anyway, so we'd like to think about how to induce a Riemannian connection. It's like on M, it's like given a Riemannian connection on M bar. Okay, so let's consider what we need. So you need to, when you apply, it's like the Riemannian connection, it's like you need a tangent vector and you need a vector field, right? So so let's say that we have a tangent vector, it's like on M, okay, and a vector field on M again, right? So so the first thing to do, of course, is to think of these things, it's like as tangent vectors and vector fields on M bar first. And when you do that, of course, it's like then you can use the Riemannian connection nabla bar, it's like on M bar, it's like to give you something. Okay. So, okay. Okay, so given this, right, since Txm is a subspace of Txm bar, right, you let this eta bar, right, be sort of this eta viewed as an element of this larger space. Or if you prefer, it's like, again, it's the tangent lift of the inclusion map. Okay. Okay, and then now you have a vector field. It's like on M. You have to look at a smooth extension of this. It's like to M bar, right? Okay, so could C bar be a smooth extension? Well, smooth local extension. So you just need this in the vicinity. It's like of M. Okay. And so you just actually need to do this over coordinate neighborhood. U of the base point x, right, in M bar. All right. Now we're in a position to look at how the Riemannian connection nabla bar acts on these sort of the inclusion. It's like of the vector. It's like and the smooth extension of the vector field. Okay. So you look at this. Okay, so what I'm going to do, of course, is I'm going to define it's like the action, if you will, it's like of the Riemannian connection on M bar. It's like on this data to be nothing more than the Riemannian connection on M bar applied to, again, the inclusion. It's like of the vector and the smooth extension of the vector field. Okay. All right. So, so the claim is that this doesn't depend on the local extension. Of the vector field. Okay. But in general, the problem is that this is only an element of the tangent space to M bar, and it's not necessarily an element of the tangent space to M. Okay? All right. So, okay, so let's see. So, but in general, right? Nabla bar of this, right, is an element of the tangent space to X of M bar, but not necessarily sort of an element of the tangent space to M. Okay, so so of course you need this to actually, or you need something which is an element of the tangent space to M and not just the tangent space to M bar. It's like for this to then give you a Riemannian connection on M, right? But what you can do, of course, is that if you have a Riemannian metric on M bar, right? So if again, sort of, if you draw a picture, right? If you think of this as M bar, and you think of something like this as M, right? There is, you know, there's the tangent spaces at x to m, right? And you can define, if you will, it's like a subspace which is complementary to the tangent space to M. And you can define that split using the Riemannian inner product, right? So you can use the Riemannian metric on M bar, right, to define a decomposition which is follows, right? Tx of M bar, right, is nothing more than Tx of M direct sum Tx M perp, if you will. Okay, and the perp is with respect to again this Riemannian metric. Okay, so in particular that allows me to write any vector, right? So this allows me to write any vector in the tangent space to M bar, right? If x is also on M, right? Uniquely as a decomposition, right? So there's a projection at x, it's like of this plus some perpendicular projection of course, this is in the appropriate space. This is in Tx of M, and this is in Tx M perp. Right. Okay. So so that sort of presents sort of the obvious thing to do, right? So you have nabla bar of it's like of this data. It's like which is in M. Right, but this is of course an element of Tx M bar. Okay, and if you want it to be an element of Tx M, you can apply the projection to it. Okay, so to obtain an element of Tx M, right, you can apply this projection, this orthogonal projection. And the orthogonal projection, again, is with respect to this Riemannian inner product. Okay. All right. So you have the following result. Okay. So let me state the following proposition. All right. So you let M be a Riemannian submanifold. Of a Riemannian manifold M bar, okay, and let nabla and nabla bar denote the Riemannian connection on M and M bar respectively. Okay, then the following is true, right? Then I can define basically a Riemannian connection in M bar as just a projection of this object here, which I defined by the inclusion of the vector, right, into M bar, and the inclusion, well, the smooth local extension of the vector field into M bar, and then applied the Riemannian connection on M bar to that, right? So okay. All right, so this tells you that the Riemannian connection on M is actually obtained in this way. Okay, so for all vectors for the first slot and vector fields for the second slot. Okay, so of course, you know, when this is most useful, right, is when the Riemannian manifold, which you are embedding M into, this M bar, right, is say Euclidean space. And the reason, of course, if M bar is Euclidean space, then the Riemannian connection on this is just a classical sort of connection, which is just obtained by the classical directional derivative. And so this particular expression, it becomes very easy. You just apply the classical directional derivative, and then you do the projection onto it. Okay, so let me just state that as a remark. Okay. So this result is particularly useful. When M is a Riemannian submanifold of Euclidean space. Okay, then we get that the Riemannian connection, it's like on M, right, is just going to be the projection, right, the orthogonal projection of the classical directional derivative. Okay, so that is nothing more than the classical directional derivative followed by orthogonal projection. All right. So this is particularly easy to compute, right? Yeah, and you know, again, it's like you know, many of the applications which we're looking, this is indeed the case that they have. You can think of these manifolds as Riemannian submanifolds of Euclidean space. Okay, and again, that makes your life much simpler. So let me just stop here for now, and we'll continue in a little bit.